Another problem from Graduate Math Solved. Now you can find us on YouTube, Instagram, and Twitter. Please subscribe on all platforms so you get notified of our new videos that keep coming on a daily basis. So today we have a family of functions from a metric space into real line, and they are uniformly bounded and equicontinuous. The question is to prove that G defined by this supremum is a continuous function. So let's see where we begin. If you have forgotten the definitions of equicontinuous and uniform boundedness, they will be apparent from the solution that I present. So number one thing that I want to show is that this G is indeed a function. So G from X into R is well defined. Okay, do I really need to worry about this? Yes, because I'm taking a supremum over an arbitrary family. How am I sure that this is not infinity? And that's where the uniform boundedness comes in. So by definition of uniform boundedness, there exists some non-negative number m such that for every function in my family, for every x in my metric space, f of x, this real value is bounded in absolute value by m. As a result, g of x is a real number. In particular, it's not infinity or negative infinity, so it is in there. So that makes it a function that really maps into real line. Now let's get to the continuity part. So, well, there isn't much you can do because you're on a metric space, so that actually makes things easier, because you have to try the only thing that has to work, and it has to work because there are no other choices. So given epsilon positive, so I will go all the way back to definitions. So given epsilon positive, we will find delta positive such that for every x in your metric space X, for every y in your metric space X, the following holds. Distance of xy is less than delta would imply g of x minus g of y is less than or equal to epsilon. So this is enough. So so this is exactly continuity. Well, maybe this equality sign is here, but epsilon being arbitrary, it doesn't matter. We will find delta such that this happens. This will show, if we succeed in doing this, that G is actually uniformly continuous. With that meaning that the delta we find is independent of the x and y. So we don't find a delta at every x. We find a uniform delta for all x's from my metric space. So actually, I'm going to show more than the question asks for. But how do you prove the claimed statement? Let's call it star. To show that this claim holds, choose. So again, I'm having some issue with my Apple Pencil. I'm not sure if it is from the app I'm using to write on or from my pencil. I'll get to the bottom of this to show star, choose delta positive from equicontinuity. So because the family is equicontinuous, so that there is a delta such that for every f in the family, for every x in x, for every y in x, x distance of xy is less than delta implies that f of x minus f of y is less than epsilon. That is by definition of equicontinuity. From this, we get that f of y is less than or equal to f of x plus epsilon. But notice that f of x is less than or equal to supremum of all f of x's from this, which is my g of x. So if this is 1 and 2, from 1 and 2, I get the following, that f of y is less than or equal to g of x plus epsilon. So 1, 2, and 3 are all true under this choice. So it's for all, of course, and the distance of x and y being less than delta. So 1 and 2 and 3 hold under these assumptions. Now here we have something. This side is a quantity independent of little f. There is no f in it. We have considered all f's and taken supremum. So this quantity per se is not technically dependent on any f. So we have this for every f. From my family, I have this. As a result, if every single element is less than an upper bound, taking supremum, so taking supremum, we get that g of y, which is supremum of fy's, f being from the family, is less than g of x plus epsilon. This is 4. And now I have that g of y minus g of x is less than epsilon. Something interesting here. So this is true as an abstract inequality, right? So it all comes from this here, that this is not equality and these are not equalities. But when you take supremum, even if these are abstract inequalities, you still can get equality. So that's why we had to include the epsilon, the endpoint. So you have proven that for every, so we have proven that for every y, if distance of y x less than delta, you have this, right? Don't forget that y is arbitrary. But y and x are arbitrary, of course, except for distance of y x less than delta. So we must also have, or you could say run this argument again with y and x switching roles. that g of x minus g of y is also less than epsilon. So this is just negative of that. So if this is 5 and this is 6, by 5 and 6, not by, they're just together combined into the following, that g of x minus g of y is at less than or equal to epsilon. If something is less than epsilon and its negative is also less than epsilon, so in absolute value, it is there. And that ends the proof. So for every epsilon, remember this is for every x and every y, distance y and x less than delta. So that is exactly what we needed. And this is by definition saying that G is uniformly continuous. So if you like this solution, please like and subscribe to the YouTube below. And if you have any questions about this problem and its solution, please put it in the comments. I do my best to reply.